Hi ladies and gentlemen, in the last video we have seen a ripple counter, that's a 3-bit ripple counter and 3-bit up-down ripple counter. Now in that we have seen that the number of count cycles, that is a power of 2, either a power of 3, 2 raised to 3, that is 8, or 2 raised to 2, that is 4, or mod 16, that is with 4 flip-flops. Now in this video we see a counter with any modulus. Suppose I want a mod 5 counter, that is I need 5 counting cycles. How do I do that? So this I do with the help of the reset terminal. So let me start with that presentation. Now the speech is organized into your learning outcomes, then a mod 5 ripple counter, a mod 5 counter with a Verilog, and a mod 5 counter with a latched reset and its implementation in QUCS, and mod 5 counter with a Verilog, and then the summary of understanding. So what you will learn in this video is that you will learn the implementation of a mod 5 ripple counter using flip-flops, and you will realize them in QUCS and Verilog. Then you will learn the need for latching of the reset signal. So how do I do a mod 5 counter? That is, it will have the counting cycles from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Then when it starts when it's about to count 1, 0, 1, I am resetting the old flip-flop so that the next count will be 0, 0, 0. So, but you need some modification for that reset signal. That is, you will understand the need for latching the reset signal. Then you will implement a mod 5 counter with a latched reset with QUCS and Verilog. So modulus of a counter can be made other than a power of 2 by selectively resetting the counter. So here I'm talking about an up counter, and I'm using the reset terminal, the asynchronous input reset terminal, to reset this flip-flop when the necessary count is reached. For example, a mod 5 counter results if all the flip-flops are reset when the count goes above 100. So I have 5 counting cycles, that is 000 to 100. After that it should count 000. So also when the counter goes above 100, when it's about to count 101, I have to generate a reset signal and clear all flip-flops so that it starts counting from 000 again. So we have to generate a low reset signal when it counts Q2, Q1, Q0, that is 101. So how I can do is I can implement this resetting signal with a 2-input NAND gate with Q2 and Q0 as the input, and that circuit diagram looks like this. Here I have 3 T flip-flops. These are actually T flip-flops. This is connected to logic 1. The 1 is not really visible there. These are T flip-flop with J and K connected to 1. Here these are all positive edge triggered flip-flops. So for up counting, I have to connect a Q bar to the next clock. So here also Q bar is connected to the next clock. And these are the outputs Q0, Q1, Q2, and this Q2 and Q0, they are ANDed here. They are NANDed here actually. This is Q2 and Q0 are NANDed here, and they are the output of the NAND is connected to the common clear terminal. Okay, the clear terminal is common, and this is connected to the output of this NAND. So when it counts like 000 to 100, one of these Q0 or Q2 is low, making this reset signal, making the output of this NAND get a 1 always. So that time normal counting happens. But when it's about to count 101, after 100, when it counts 101, what will happen is these two inputs to this AND gate, both inputs are 1, making this output 0. So that is given to this clear terminal. So this all the 3 flip-flops are cleared. When it is about to count 101, all the flip-flops are cleared. So after 100, the next count will be 000. So it again starts counting from 000, 001, etc. So I will show you this simulation in QUCS. Here, this is the circuit diagram. Here, all the T's, 3 T flip-flops are there. All the T's are connected to one, and the first flip-flop is driven by a clock. That is a low for 10 nanosecond and a high for 10 nanoseconds. And other clocks are derived from the previous Q bar outputs. So this Q bar is connected to the next clock. Here, this Q bar is connected to the next clock, and this resetting signal is generated like this. This is Q2 and Q0 are NANDed, and the output is fed to the reset terminals. So let us see this simulation. So here you can see the waveforms. This is my clock. That is, I will start from the beginning. So the clock is low for 10 nanosecond and high for 10 nanosecond. So at the first leading edge of the clock, Q0 toggles, and at 30 nanosecond again it toggles, and at 50 nanosecond it again toggles. That Q0 has a frequency half that of the clock, and Q1 has a frequency half that of Q0. But here, as it counts from 000, 001 or 011, 100, now when it counts 100 up to that it is fine. Then this is 100. After that, what happens is the reset goes low, and all the flip-flops are cleared. Here you can see that here the resetting signal comes, and at this point at 90 nanosecond the resetting signal comes, and this all the 3 flip-flops are cleared, and now it counts 000, again it counts 001, 010. Then here at this point you can see that again there is a reset signal. After 5 counting cycles, there is a reset signal making Q2, Q1, Q0, 000. Now, if you look closely here, you can see that you cannot actually see this reset signal here. There is a reset signal here, but you cannot easily see this. Why? Because it occurs for a very short duration of time. Here in this graph, you cannot easily observe this reset going into 0. The reset, you can see that's a high from here to here. Here it goes low, but you cannot easily view that. Because it happens when as soon as it starts goes to 101, the reset is created. A reset signal becomes low, and when the reset signal becomes low, all flip-flops are cleared, and it starts counting 000. So as soon as it starts counting 000, the reset signal disappears. So that's why you do not see this reset signal. Now there is a problem with this. That is, the reset delays are different for different flip-flops. So the resetting delay, that is the propagation delay from the reset terminal to the output Q, that may vary in flip-flop. So in one flip-flop it may be 1 nanosecond, in the other it may be 2 nanoseconds. So if the resetting time or the clearing time is different in different times are different in different flip-flops, then it may happen that one flip-flop is cleared and the other flip-flop is not cleared. So if one flip-flop is cleared, then the resetting signal will be over, will go to high, and the other flip-flop may remain uncleared. So then you may start with the wrong count. For example, if you look into this diagram, suppose this Q0 is cleared and Q1 is not cleared, Q2 is not cleared. So what will happen is when it counted 101, this signal came, and Q0, the first flip-flop is cleared, but the third flip-flop is not cleared. So what happens is this becomes a 0, Q0 becomes a 0. So then the reset signal becomes a high again, because as soon as this input goes low, this output goes high. Now the resetting signal disappears. So but this hasn't been cleared. So what happens? This remains in 1. Okay, rather than 0. So what happens is, instead of having 000, you will have a 100, which is a wrong count. Okay, so next cycle, when the next clock arrives, what will happen? It will start counting from 100 onwards. Okay, so or else if this is cleared and this is not cleared, so it can happen that way. Then what will happen? It may start with the wrong count, say 001. Okay, so instead of starting with 000, I will be starting with 001. Or if this is not cleared, these two are cleared, I may be starting with 010. Okay, so what the problem that happens here is the resetting signal is not wide enough. Okay, it doesn't stay, it has to stay for sometimes say half the clock cycle, it has to stay. So I have to make some modification in this resetting arrangement. But before I make that, let me see how a Verilog model is made. A Mod-5 counter with a Verilog. So uh, the, this is pretty simple. What I have to do is I have created an edge triggered flip flop layer, edge triggered flip flop. So that is grave include JK f of edge dot v, or else I will show you this code that will be more easier. So this is my counter. So this is so first I include the JKF of edge dot v, and I start with a new module, a Mod-5 counter, n module. This Mod-5 counter outputs are Q bar, inputs are JK clock, reset and preset. And the output Q and Q bar, they are 3-bit wires, so that is 0 to 2, 2 to 0. They are Q and Q bar are 3-bit wires, and the inputs, other inputs are wires, JK clock, reset and preset, they are input wires. And this is the local net or internal net, that is the output of my NAND gate that I declare as wire A. Then what is this wire A? That is a NANDed output. What is NANDed? That is Q0 and Q2 are NANDed, because this is the output of the first flip-flop, this is the output of the third flip-flop. Okay, so as soon when it counts 1 0 1, this A will become a low. Okay, so that's a NAND gate. Then I make 3 instances of my JK flip-flop. Even though in this file I have the device is JKF of pos edge, I give some name. So its output is Q0 and output is Q0 and Q bar 0. Inputs are JK and clock. This is the external clock, and clear is connected to A. That is the output of the NAND, and a preset. Okay. Preset is not used here. Here in this is the second instance of the JK flip flop. Here the outputs are Q1, Q bar 1, JK, and clock is the Q bar output of the previous stage, that is Q bar 0. Then clear is A and preset. Now there is a third flip flop, that is JKF of 3. Output is Q2, Q bar 2, JK, and clock is Q bar 1. That is the Q bar output of the previous stage. Then A and preset. That ends the module. Now I can make a test bench here. Now here I make a I include the Mod-5 counter. I create a test bench. Then inputs JK clock, clear, preset, they are given as registers, and Q and Q bar are given as wires, 3-bit wires. And I make an instance of the Mod-5 counter, say C1, name C1, Q bar, JK clock, clear and preset. And then I initialize a monitor. Okay, then I dump this waveforms into a Mod-5 counter.vcd. And then I apply the clocks. Initially I use this thing to preset this. Okay, it is initially preset, it is preset to 111. Initially it is preset to 111, then it starts counting from there. So then you apply clock in every 5 seconds, and finally I end the module. Finish and end the module. Now let us run this simulation with Verilog and observe what happens. Minus O A dot out. Okay, now I have to run this A dot out. Now you can see that this counting pattern. Initially I have preset. Initially the at 0 nanosecond preset equal to 0. So the count starts at 111. Okay, and at 5 seconds what will happen? The clock is 0, so it remains in the previous, it remains in an arbitrary value. And here the clock is 1, and it starts initially this is cleared at that is with a Q equal to 0 and a Q bar equal to 111, and at 10 seconds the clock is high, and it counts 001, the first count, then 00010 at 20:001, then 0100111100. After 100 it doesn't count 101, instead it counts 000, because this is cleared by the reset signal. Now again it starts counting 001010, that way. So you can observe the 5 counting cycles in this. Now let me go back to my presentation. Now, how do I overcome my earlier limitation? That is, my reset signal is too short. So, what happens is the resetting delays may be different for different flip-flops, and if the resetting signal is not wide enough, then it may result in false resetting or erroneous clearing of flip-flops. So this false resetting will result in wrong count sequences. So that difficulty is overcome by latching the reset signal for half the clock cycle. So you can see that in between this NAND output and the clear terminal, I connect a latch that is also driven by an inversion of the clock. So that what is the purpose of this latch? This reset signal that comes here, that is when it counts 101, a low reset signal comes here. Now this remains here for half the clock duration. Okay, this reset signal remains here for half the clock duration. Half the clock duration is fairly large enough to clear all flip-flops, because the clearing delay is usually much smaller than the clock duration. So what this latch does is it ensures that the resetting signal stays at this resetting terminal, this common resetting terminal, for half the clock cycle. So this is how I overcome the problem of false resetting. So let us see this simulation in QUCS. Now you can see that this is a realization of that circuit. Here the clock is inverted and is given to this latch. This resetting signal is given to the other input of the latch, and the output of the latch is given to the common reset terminals. Now let us see the simulation. Now you can see this reset signal. Here the counts are here 000, 001, 010, 011, 100. After that it resets. Okay, now you can see that this reset signal stays here. This is my reset signal. Earlier you couldn't see this reset signal going low, but here you can see that it goes low here at 120 nanosecond. It goes low and it stays there for around 10 nanoseconds. Okay, this stays low for 10 nanoseconds. So during this time all flip-flops will be cleared, so you won't have any problem of wrong resetting of flip-flops. So here you can see that all flip-flops are cleared. It counts 000, 001, etc. Okay, so this way I can avoid a false resetting. You can clearly see the reset signal that stays low for half the clock duration. So this way I solve the problem of false resetting. Now you can have a Mod-5 counter with latch in Verilog. You can see this. This is a Mod-5 counter with latch. Here also I include my JKF edge. I start a module. Other things are the same, but here I make a latch like this with the help of this NAND NOT. Here this NOT gate is used for inverting the clock, and here these NAND gates they are used for. This NAND gate is used for. This is my first NAND gate. This is for creating the reset signal from Q0 and Q2. This A is Q0, NAND Q0, Q0 Q2, Q0 and Q2 all complement A, and these two NAND gates, this realizes my latch. Okay, so here I have a test bench for this. That is a Mod-5 counter with latch. Now I can run this and you can appreciate this. Now you can have a test bench for this. -O A dot out. I can run /A dot out. Now you can see this count cycles. Initially it is in 111, then it goes to 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, then goes to 1, 0, 0, then it clears to 0, 0, 0. Here the reset signal is created, so 0, 0, 0, 0, 0, 1 that way. Okay. Now you can see these waveforms. I can use GTK wave, this dump file. Now you have this test bench here. I can see this clock, the clear signal. I don't need JK because they are kept at 1. Then Q bar. I can append them. Okay. Okay, here you can see that at this point it clears. Okay, this is from 1110010 to 100, then it clears. Okay, I don't know how clear that how wide that clear signal here is. Here the count cycles are from 000 to 100, then 000 to 100, and again. Okay, now here the clearing happens. Okay, you can observe these waveforms this way. Now let me go back to my presentation. So now what you learned in this video is that you learned the Mod-5 ripple counter and simulated with the QUCS and Verilog. Then you understood the need for latch resetting to overcome false resetting. Then you simulated a Mod-5 counter with the latch resetting with the QUCS and Verilog. And that is the end of this presentation. I thank you all.